Berlin, Germany. Autumn 1943. According to widely repeated but officially unverified accounts, an American technical observer named Thomas Halden walks out of the British Air Ministry's Berlin analysis cell carrying something that, if properly understood, could change the course of the Allies' rocket research. If anyone listens, he's holding a twisted, charred fragment of a German V-2 rocket fuselage, about the size of a man's forearm, still warm from the impact crater where it was recovered. Along its edge runs a smooth, uninterrupted weld seam, deep, uniform, and deceptively simple. To most people it is nothing but scorched metal. To Halden it is the signature of a structural philosophy the Allies have yet to comprehend. According to those accounts, Halden had spent months assisting British intelligence in cataloging debris from German long-range rocket attacks. He'd watched analysts measure fins, sketch engine bells, weigh fuel tanks. He'd seen propulsion specialists debate ethyl alcohol mixtures and turbopump efficiencies. But almost no one paid serious attention to the body of the rocket itself. The long steel shell that had to survive violent vibrations, crushing aerodynamic loads, and the brutal physics of supersonic flight. The Germans did. And they built it differently. Halden boards a flight back to London. He brings several fuselage fragments with him. He brings photographs of weld sequences found in captured workshops. He brings technical notes taken from British examination rooms. He believes he's carrying the key to a rocket design the Allies desperately want to understand. He believes the United States will want to hear what he's found. He believes they will recognize the significance of something as mundane as a weld seam. They won't. The Americans will reconstruct the V-2. They will document every visible feature. They will copy the layout, the fins, the tanks, even the guidance compartment geometry. And then, in one quiet decision hidden deep in an engineering office in Ohio, they will change the one detail that cannot be changed, the welding method. That decision will turn a stable German design into an unstable American one, cripple post-war rocket tests, and set back early U.S. missile development by years. Not because the Americans misunderstood the fuel. Not because they removed the fins. But because they changed something invisible, something that looked like a harmless manufacturing shortcut, something no one thought mattered. The weld. This is the story of how American engineers looked at German rocket perfection, kept all the obvious features, changed one hidden detail, and created years of structural failures that would haunt early American rocketry from 1945 to 1951. Peenemünde, Germany. March 1942. In a vast windswept test facility on the Baltic coast, German engineers test the world's first operational ballistic missile. The V-2 is huge, 46 feet tall, 28,000 pounds, capable of reaching supersonic speeds and arching into the stratosphere before falling on its target at nearly Mach 3. But its engine, revolutionary as it is not the most difficult part. The hardest challenge is keeping the rocket together. At throttle, the V-2 vibrates so violently that early versions shattered. The shell buckled. Panels folded like paper. The rocket ripped itself apart in midair. So the Germans redesigned the fuselage. They tested steel alloys. They tested ribbing patterns. They tested heat treatments. And eventually they discovered that the rocket's survival depended on one thing above all. The body must act as one continuous structure. Not a collection of plates. Not a patchwork of parts. One tube. One resonant piece. To achieve this, they developed a continuous deep penetration welding process. Two long curved panels, stamped into shape, were placed edge to edge and fused in uninterrupted passes. No stop-start segments. No stitch welds. No shortcuts. The welds were not decorative. They were structural. They absorbed vibration. They prevented resonance. They spread thermal stress evenly. They turned the rocket into a single tuned instrument rather than a clattering assembly of plates. German testing showed dramatic improvement. Rockets that previously shook themselves apart now held together. They survived launch. They stayed stable through max Q. They reached their targets. The V-2 remained dangerous because the weld remained perfect. The Allies don't realize this at first. Through 1944, teams in London and later in France collect fragments of V-2s that overshot or failed. They catalog hundreds of pieces. They test fuel mixtures. They reverse-engineer turbopumps. They interview captured technicians. But the welds, the quiet structural foundation of the entire rocket, remain largely unexamined. When the U.S. Army begins planning to replicate captured V-2s for post-war research, they focus on the big components: chambers, turbines, tanks, fins, guidance units. The shell is treated like any other piece of sheet metal. Shape it, rivet it, weld it where needed. No one considers that the body of the rocket is not just a container. It is a dynamic, vibrating resonance system. Wright Field, Ohio. Summer 1945. Captured German components arrive by the crate. Engineers lay them out on long tables. They study the aerodynamic profile. They admire the welded joints. They note the uniformity. But then the manufacturing department steps in. Continuous welds require specialized equipment, careful heat control, uninterrupted work cycles, and skilled welders. They are slow. They are expensive. They require tooling American factories don't have. But there is an alternative: segmented welds. Shorter. Faster. Using equipment already in use for aircraft and armored vehicles. Perfectly adequate for anything that doesn't vibrate like a rocket. So the Americans redesign the fuselage construction. They keep the shape. They keep the thickness. They keep the length of the shell and even the placement of internal stiffeners. But they replace the continuous German weld with a patchwork of stitch welds. Dozens of small segments, slightly overlapping, cooling unevenly, creating tiny variation points. Almost invisible. And catastrophic. Testing begins in late 1945 and early 1946. The first American-built V-2 replicas shake. They rattle. They flex in ways the German originals didn't. Instruments show resonance spikes at surprising frequencies. During static firings, the structure hums like a struck bell. During flights, some rockets veer off course, others disintegrate, others collapse under aerodynamic stress. Engineers blame engines. They blame fins. They blame guidance. They blame fuel mixtures. Very few blame the shell. After all, the shell looks identical. But the weld is different. By 1947, after dozens of failures, analysts begin examining structural vibration data. They compare the American rockets to surviving German ones. They notice the difference. The welds behave differently under load. Each stitch weld creates a discontinuity, a hinge point, a place where waves reflect instead of dissipating. The rocket becomes a collection of vibrating plates instead of one unified column. The Germans had discovered this in 1938. The Americans rediscovered it 10 years later. The internal reports accumulate. Some engineers argue the German weld method must be reinstated. Others insist the American method is good enough. Manufacturing contracts resist any change. Budgets are locked. Tooling cannot be replaced easily. And so early American rockets continue to fail. The issue is not publicized. It becomes a quiet engineering embarrassment buried in classified documents. Meanwhile, in Peenemünde, as the war ends, Allied troops capture not only parts but full documentation: weld schedules, heat treatment charts, vibration reports, resonant frequency analyses. The Germans were meticulous. Their notes show that early V-2s with segmented welds failed catastrophically, and that continuous welding became mandatory sometime in 1939. The answer had been written plainly in captured files months before American engineering teams had finalized their redesign. But no one had read them closely enough. By 1948, the U.S. finally transitions to continuous welding for rocket fuselages. Testing stabilizes. Failures drop. Rockets fly straight. The American missile program begins to advance. But the years lost to the invisible weld decision linger in the background of early Cold War rocketry, forgotten by the public and rarely acknowledged in official histories. What is documented is this: German rockets succeeded not because of a single revolutionary breakthrough, but because every detail mattered. The continuous weld wasn't decorative. The shell wasn't just a container. The rocket's survival depended on structural unity. American engineers copied every visible feature of the German design and changed the one invisible feature that mattered most. They assumed segmented welds would be good enough. They assumed manufacturing shortcuts wouldn't affect performance. They assumed the details didn't matter as much as the design itself. They were wrong. And while precise statistics of failures caused specifically by segmented welds remain unclear, buried in classified test logs and fragmentary reports, the consequences were measured in crashed prototypes, delayed research, and engineers forced to relearn lessons their adversaries had already mastered. The modern rockets used today, from ballistic missiles to orbital launchers, still carry the German insight. Their bodies are welded in continuous seams because that is what works. Because small details matter. Because shortcuts have cost. Because sometimes the best thing you can do is copy someone else's brilliance exactly as designed. Thanks for watching.